Hello, I'm Francisco Girela. I am the lead technologist at Seven Solutions, and this is timing monitoring following the White Rabbit. So first of all, a little bit of background on time synchronization. So time synchronization is the capability to maintain a shared notion of time between different devices that are placed in the same or different locations. And we say that it is traceable when we are able to compare that notion of time to an official notion of time. In order to get time synchronization, we can rely on generation of timing or distribution of timing. Generation will be getting that notion of time from an external device, like for example a GNSS time server or an atomic clock that are generating their own time scale, and distribution will mean propagating that notion of time to different devices in a network. For example, using time synchronization protocols like NTP, PTP, White Rabbit, or other techniques like analog distribution using PPS. In order to describe time synchronization, we typically use accuracy and precision. Accuracy is the degree of correctness in the time synchronization. So if we are comparing the clocks in two different devices, when we have a time error close to zero, we say that the time synchronization is accurate. But time is dynamic, and that means that it evolves. So we can measure at a later time, and we can have a time error which is different. If we see that after many measurements, this time error remains constant, we say that we have a precise time synchronization. However, if we see that there is a variation on that time error, that will mean that we have a low precision time synchronization. For example, if we check the graph here with a PTP and White Rabbit comparison, we can see that both of them are accurate. Why? Because the comparison between the clock or the time in both devices is close to zero or centered in zero. But we can see that White Rabbit is much more precise because every time that we check the time error, the dispersion between those measurements are lower than the ones in PTP. So White Rabbit is an implementation of a standard PTP, which main goal is to achieve sub-nanosecond accuracy. So White Rabbit can be integrated in Ethernet network, the same that standard PTP, is interoperable with previous PTP implementations, version 2, for example, and other protocols like NTP or other techniques like PPS distribution. We can say that it is resilient to GNSS disruption because it is not a generation technique, it's a distribution technique. So we are distributing or propagating the time using fibers. And it has some specific techniques that allow this technology to achieve this sub-nanosecond accuracy, avoiding expensive calibrations and being able to reach devices that are far away in metro area distances or even wide area distances and scale to thousands of nodes. Actually, White Rabbit is the high accuracy profile in the latest revision of PTP, the version 2.1 version. It is important to have some knowledge about the White Rabbit hardware. The White Rabbit hardware has some particularities. For example, they are typically multi-port devices because this way we can deploy point-to-point White Rabbit links that will ensure the best accuracy. But these ports, these optical connections, can be used to also distribute other protocols like NTP or PTP. At the same time, having multiple ports allow these devices to have multiple timing references coming to the device, and therefore we can have failover mechanisms to go from a time source to another in case of failure, or even to internal holdovers. So they are pretty similar to PTP devices, regular devices. Additionally, the White Rabbit devices provide analog timing inputs and outputs to retrieve time from external time servers, for example, an EPRTC or an atomic clock, and also to provide analog signals. In order to deal with the failover feature in the white rabbit devices, we have the failover algorithm. So in the failover algorithm, what we do is to assign priorities to each one of the time references in the device, and we only switch from one reference to the other in case of failure or manual configuration. That way we avoid automatic failovers because of that are kind of uncontrolled to the operator. Keep in mind that we are going for a high accuracy time synchronization, and we need to keep control of what's happening in our timing network. So we will have multiple timing sources in one device, one algorithm that selects which one of them is the active, looking at their priorities, and also telling our device if we need to jump to another time source. This time source will be the one that we use to discipline the internal oscillator in our device, and the one that we will use also to distribute timing to the subsequent layers in the time synchronization network. So we have a time synchronization network, and we know that we cannot rely only on GNSS, because we know that there are jamming, spoofing, interferences problems. We cannot just rely on the network, because we can have problems with the fiber. So at the end, we are building pretty complex systems where we have different position, navigation, and timing technologies coexisting in the same timing devices and the same timing networks. And that leads to dealing with higher complexity, with higher diversity. We need to take care of the integrity of all the different timing sources that we have. And at the same time, we see that we need to have a traceable notion of time, because we need to report, or because we need to coordinate the timing between different locations. And also, the accuracy requirements are improving, or are getting higher and more strict. And for that, we need timing monitoring. So we have this technology, which is White Rabbit, high accuracy time synchronization. So why wouldn't we use that time synchronization to perform high accuracy measurement of all the different timing sources that we are receiving in the device? So we have collected all that information using or combining LLDP information, reverse timing collection, multiple protocols taking advantage of the interoperability of the devices, and all of them in just one single centralized device. So it's easy to get or retrieve all the information on that timing comparison. And as we are having this high accuracy reference, which is provided by the White Rabbit, then we can measure with high precision all the different inputs, and also with a high frequency sampling, so we don't miss any event of interest. For that, what we do is to define different roles in the device. We have the active timing source, which is the one selected by our algorithm to command or to discipline the internal clock in the device. We have the passive timing source, which are the ones that we use in case of failure to jump to them, but we also use to monitor the time that we are receiving from them. And lastly, we have the survey timing source, which is a timing source that we don't want as a reference in our devices in any case, but we still want to keep track of the timing that we are receiving through that interface. And thanks to that, we are able to retrieve different statistics, like for example, the offset, the time error in the synchronization, the delays in the link, the standard deviation, the maximum and minimum offset that we are feeling, and even correlate that information with the temperature that we are measuring. If we are dealing with a local area scenario, imagine that you have two different sources, GNSS receiver, and atomic clock. Then we have a layer of devices that are the fan-out layer that later provides this timing to all the different devices in the network. So we have in the fan-out layer, failover capabilities, rollover in case that something fails. But what we can also have is here, for example, a centralized node that collects all the information, not only from the upper layers, but also from the lower layers. So if we close loopbacks, as we have multiple ports, we could be measuring here all the time synchronization in the whole network. And that's important because thanks to the White Rabbit accuracy, what we will have are pretty good measurements of all the different time sources that we have, because the sub-nanosecond accuracy of the White Rabbit almost guarantees this zero time budget consumption on the measurement. And the same applies when we are speaking about wide area scenarios. We have different sites, we have cesium clocks, we have GPS receivers, and we have all the distribution network to all the different sites. And after that, we have also the local distribution in each one of the sites. So what we could do is not only having this backup to GNSS because of the distribution over fiber and the failover mechanisms, but also some loopback links that will allow us to measure how good is our timing in the different locations, also to check or to calculate asymmetries and offset and the effect of temperature. So a pretty interesting solution to have a centralized point of measurement. And in a wide area scenario, this is even more important because we are not anymore dealing with just a single time reference. We are dealing with different time references that could have problems with the calibration of the delays. For example, in the GNSS receivers that are far away, we can have asymmetries in the fiber links that will lead to an inaccuracy on the synchronization. So having White Rabbit at least is an accurate way to adhere to one of or at least to your reference. So you will have the sub-nanosecond accuracy, and then you will be able to measure with a better precision the potential asymmetries that we have in the fiber link, or the potential calibration issues that we have because of the delays in the GNSS antenna or the GNSS cable connecting to the GNSS receiver. Finally, we have this use case that I wanted to present, which is in the Spanish Stock Exchange. In that case, we were synchronizing two data centers which were 27 miles apart. We had redundant time references feeding the White Rabbit network, and that White Rabbit network was distributing time through a 27 miles link to a different data center. And on the second data center, we had a GNSS discipline oscillator, which also provides White Rabbit. So we were able to provide traceability to the time information that we were receiving here. And the accuracy that we were able to achieve was the one that the GNSS receiver was providing, because in that link, or in this link, and in the comparison, we were maintaining the sub-nanosecond accuracy. Additionally to that, we included some rollover capabilities that we could use also as a backup reference. So that's all for me today. Thank you for your attention, and if you have any questions, please feel free to contact me. Bye.